It's our pleasure today to have Duncan Clark from Ohio State University, who will tell us about an intrinsic operad structure for the Goodwillie derivatives of the identity.
Thanks. Thanks for the invite, and thanks to everyone for being here. It's a good opportunity to get to give this talk. So I assume that not everyone is an expert in Goodwillie calculus. So there will be enough lead in to sort of make sense of what this statement is really telling us. But the sort of main idea behind this whole talk is that the Goodwillie derivatives of the identity should come equipped with canonical operad structure. So the identity functor where, well, I'll just denote this by C, and then I'll say, for instance, when C is the category of pointed spaces, the category of spectra, or more specific to what I'll be talking about today, the category of algebras over some operad O. It's also expected that this should work for more general categories, but today I'll focus on sort of these examples. So, where is this coming from? Well, the first instance of this kind of structure is due to Michael Ching. So what Michael Ching shows is that the derivatives of the identity in the category of topological spaces is an operad. And I will say more about this in time. But what I'm going to talk about today is my work, which shows that the derivatives of the identity in the category alg O is a homotopy coherent operad. I'm putting that in quotes because I won't exactly make that too precise, but it's meant to just be an operad, just like an A infinity monoid kind of operad. And this is my work. And I should also mention that Michael Ching has a version of this. And more generally, you can do this as Ching shows for a suitable infinity category, you get an infinity operad structure is an infinity operad. That's also due to Ching. Okay, so let's go ahead and get started. So this is what we'll be talking about today. Let's go ahead and get started with some functor calculus. So I'll call this part one. There'll be 3 parts. Every time I've given this talk, I forgot to mention that part 1 is actually part 1. So there's just part blank and then parts 2 and 3. So functor calculus. All right. Well, let's start with a pointed space X. And we sort of know classically the Fourier impulse suspension theorem says that there's a comparison X to the stabilization of X. So this is stabilization of X. And we have some connectivity on this map here. So if X itself is K connected, then this map here is 2K plus 1 connected. It's from Fourier impulse suspension. And this map is sort of a point set map instance of the comparison between unstable homotopy groups and the stable homotopy groups, namely the homotopy groups of the stabilization. Now, Goodwillie calculus takes this idea of stabilization being a linear functor. So this guy is linear, and what we mean by linear is really that this is excisive. I should perhaps say one excisive, but I'm thinking excisive in that it satisfies the excision axiom, like a homology theory satisfies excision. It says, all right, well, if I think of this as linear, is there some way to build a quadratic approximation? Approximation to what? I think of stabilization as the linear approximation to the identity functor applied to some space. That's just X itself. And sort of ask, is there a quadratic approximation, etc., cubic approximation, perhaps, that assembles into some tower? And this is in fact true. So Goodwillie shows you how to build what he calls P2 of the identity, P3, etc. which are all functors and then give you a space when you apply it to x, which come with a map from x. And one feature of being quadratic is, well, it satisfies some condition on cubical diagrams, 3 cubes, whatever. But I'll sort of draw attention to the fact that in good cases, these comparisons here increase in connectivity. So the comparison between the identity and P2 is on the order of 3K connected, and this guy is on the order of 4K connected. And as I sort of move up this tower, in good cases, I will build back in all of the information about X. So build back in info about X. So that, when I take the limit of the tower, I recover at least the homotopy type of the space that I started with. So this is sort of an instance of a Taylor tower. And of course, Goodwillie shows us that we can do this all more generally. So I'm just going to move this over a little bit. If I start with a functor f from top to top, the only thing we really need to know is that f preserves weak equivalences. I'm going to also assume that f takes the point to something contractible. You can assign to this sort of a tower of excisive approximations, ... Pn minus 1 of f. Each of these behaves like a n-degree polynomial. I won't necessarily give a description of that, but you can sort of think of these as being analogous to like the nth polynomial from a Taylor series in ordinary calculus. And that analogy can really be taken quite far. So if I look at this tower, which each of these pieces receives a map from f and so on and so forth, well, one way to get information out of a tower is perhaps I can look at the layers. What am I adding to go from each piece to the next part? So if I take the homotopy fiber from Pn to Pn minus 1, then Goodwillie tells us that this homogeneous layer from this tower is sort of classified by a single spectrum. So theorem, this is due to Goodwillie, that the nth homogeneous layer of a functor f is of the form like so. So there's always some spectrum called the nth derivative smashed with the suspension spectrum of x n times, and then I take homotopy orbits of that object right here. So this guy is some spectrum with a sigma n action called the nth derivative. Now, why the term derivative? Well, this form right here for these homogeneous layers is supposed to sort of be strikingly similar to the homogeneous monomial that I have in Taylor series from ordinary calculus. So think of this as looking remarkably close to like the nth derivative of a function times xn, and then modding out by n factorial. You can sort of think of that as, well, I'm taking an orbit of a group with n factorial elements. Yeah, that's maybe the weakest of the analogies, but it's something there. All right. So that's sort of a crash course in functor calculus. It turns out that these Goodwillie derivatives have a lot of structure. So how about some examples of Taylor towers first? So if I work in the category of spectra, well, the category of spectra is stable. Push-out squares are the same as pullback squares. And that's kind of what our model of excisiveness is built off of. So in fact, the identity functor on spectra is just equivalent to its linear approximation. And then the whole tower just is given by, I'm stuck on there we go, by that guy right there. And that's basically due to spectra being stable. By the way, I should mention that I think something is weird with my webcam. So if I happen to just turn green for some reason, I'm not being abducted. It's just how it is. This has just started happening the previous weeks. So if I turn green, no worries.
You don't believe in aliens?
Well, we'll see. So far, they haven't abducted me. Right. So, So So in spectra, our one excise approximation is just equivalent to the identity itself. This is not true in the category of spaces. We already see this here. The one excisive approximation is the stabilization. And in fact, each of the levels of the tower is highly non-trivial. It's sort of different from ordinary calculus in that the identity is not always just a linear function. The layers were first classified by Brenda Johnson and then slightly later by Rohn and Maholwald. So
I actually have a question. Are these things are these things like, so if X is a finite complex, would these things ever be, would the layers ever be the suspension spectrum of a finite complex?
So
I guess it's not the suspension spectrum, but Q of a finite complex, or loop infinity, suspension infinity of, or does it tend to make things infinite?
I think so. I'm not fully sure. Perhaps the next thing I write might be helpful. So what Johnson and Aron Maholwald show is that the nth homogeneous layer of the identity functor on top applied to a space is always of the form, well, I take the underlying loop space of the internal mapping spectrum between something called the partition Postset complex and the suspension spectrum on X smashed n times, and then I take orbits. So perhaps this is helpful to your question here. So this gives you a complete description of these layers, at least for the identity functor.
I have no idea. Especially, I don't really know what the sigma n, the orbits would do, because those are like homotopy orbits, right?
Right. Yeah. So I think that's where you probably would lose finiteness. Okay, so this par n, this is the nth partition Postset complex. I won't necessarily have too much time to say anything interesting about this, but it's a very interesting object. It's a simplicial set built out of the combinatorial information of the set of partitions of the set 1 through n. So it's sort of remarkable that this thing is showing up in this way. It's sort of telling you something interesting about the category of spaces. And from this, it's just a calculation then that the nth derivative is always calculated from this guy dn by something called cross effects. And in this case, it is the Spanier-Whitehead dual to this partition Postset complex. So S here is the sphere spectrum. Okay, and it's this model here that Ching uses to produce an operad structure on the derivatives of the identity in spaces. Okay, but we're interested in talking about Taylor towers in categories of algebras over an operad. So Taylor towers in alg O. So for us, O is an operad in spectra. So what does this mean? We have some sequence of spectra, O1, O2, O3, blah, 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 together with action maps. So X is an element of alg O, means that we have sort of these action maps like so. So I can sort of describe n-ary operations on my spectrum by sort of being parameterized by the term O of n. So, for instance, you could have commutative guys, you could have associative guys, or you can more generally have En, which are sort of like homotopy commutative, homotopy associative, varying levels of those guys, ring spectra, etc. Now, I can't exactly consider it as an arbitrary operad. In this case, we have to work with non-unital operads, so operads whose zero-ary terms are trivial. This means, I'm sorry, not non-unital operads, reduced operads. This means that my O-algebras are non-unital. So I have a non-unital commutative ring. And just to make our life a little simpler, we will say that the one-ary terms are just the unit for the sphere spectrum S. This isn't necessary, but it certainly will make the presentation of what's happening a little simpler. So how about an example? It's always good to start off with an example. So let's look at when O is COM. So in this case, we have non-unital commutative ring spectra. And if you don't like ring spectra, you can just think rings. There's really nothing lost here in just thinking about these as good old rings, because what we end up recovering in this case is a pretty classical object. So from a T.M. McDonald, we have associated to a non-unital commutative ring, we have the X-adic or I-adic completion tower, where I take X mod X squared, X mod X cubed, X mod X to the 4, etc. Each of those receives a quotient map from X. And in this setting, this is the Taylor tower. So by this, I mean the X-adic completion tower. Well, what do I exactly mean by, X mod blah? We just mean take the quotient of the image of the multiplication by n map. That's our X mod blank. So smash product for spectra, tensor for rings, whatever you'd like. So these objects sort of naturally work in the category of O-algebras. More generally, let's see, I meant to scroll down just a little bit here. Cool. So more generally, given just an arbitrary O.
Sorry, Duncan.
Yeah, go ahead.
Just to clarify, was that a homotopy cofiber, or does it need to be a strict cofiber in some point set model of spectra?
No, homotopy cofiber.
Oh, okay, yeah. Thanks.
Yeah. So in general, if I have just an arbitrary O, well, I can build the Taylor tower as follows. So if I take O, I'm going to define a series of truncations. So this is the nth truncation of O. How is this defined? Well, if I want to look at this guy, if I want to look at its k-area operations, well, they should agree with those from O for k less than or equal to n. And I just destroy everything above level n. So this just says, if I multiply too many things, it's now just trivial. And each of these guys receives a map from O, and there are maps down just given by taking your spectrum at each level and just collapsing it down to a point. And this guy assembles into a tower. So the identity functor on alg O has a map into this guy. I should describe some of this notation here. I will, just give me 1 second. Tau 3, O, blank, blah, blah, blah. Cool. So what do I mean exactly here? Well, this circle, this is the composition product. I won't necessarily say too much about what this is, but I can view operads as, so an operad is the same as a monoid with respect to the composition product. And well, what is this thing? Tau 1, Tau 2, these are still operads. They just don't know anything about, too high of an area of operations. And this is the associated sort of change of operads adjunction. Just like if I have a map of rings, then I get a change of rings adjunction on the module categories. And I should really look at this tower and sort of think of this as saying, well, what is this bottom level doing? It's taking the O actions, it's taking these multiplication structure on X, and it's sort of co-equalizing it with the just trivializing everything at level 2 and above. So this guy really kind of just looks like X mod X squared, where I have this maybe more twisted notion of multiplication and so on. This looks like X mod X cubed, X mod X to the 4th, etc. So this is sort of a generalization of this sort of X-adic completion tower. Now, the theorem due to Harper-Hess is that this is the Goodwillie tower of the identity. So Harper-Hess, I should also mention Pereira. So this is the Taylor tower of the identity for algel. Right. So Taylor towers sort of tell you a lot about the category. Taylor tower of the identity sort of gives you this very naturally occurring filtration. In top, we started with the stable homotopy group. So I'm going to just draw in blue down here the equivalent map in top. So, you know, top, this base level is the stable homotopy groups, and it converges up to the space. Similarly, in O-algebras, this tower will converge if I throw in a zero connected spectrum. But I want to look at this bottom map. In the classic setting in top, this sort of knows about the stabilization adjunction. And in fact, this is a general phenomenon. This bottom map, whenever you have a Taylor tower of the identity, is closely related to its stabilization. In fact, you can't really tell the story of Goodwillie calculus without talking about stabilization at some point, and you know, spectra in this category. So Theorem, a description for stabilization in the category of O-algebras. So this is due to Bastera, also Bastera-Mandel. So I'll just write Bastera-Mandel and Pereira, is that the stabilization adjunction for O-algebras is of the following form. So I have a map of operads, O down to tau 1 of O. And I sort of mentioned this before. Whenever I have a map of operads, I get an associated change of algebras adjunction. It's just like a change of rings adjunction associated to a map of rings. So I have, you know, alg O, an adjunction to algebras over tau 1 of O. If I call this guy F just for notational purposes, you know, this is sort of the whatever, it's of the form tau 1 circled over O with blank. This is just the forgetful functor, which you know, forgets along the map O. But this algebra category here, well, tau 1 is just an operad concentrated at level 1, which you can show is just equivalent to being a ring spectrum. So this algebra category is really just modules over O of 1. And in our case, this is even simpler. It's just equivalent to spectra. So this category of modules, this is stable. And in fact, this adjunction here is a model for the stabilization adjunction on O-algebras. Now, just for some technical reasons, I don't exactly want to work with this adjunction. There's a trick you can do where I factor as operads this map into a cofibration followed by a weak equivalence. And it's really the comparison between O and J. So J is just kind of like a fattened up version of O of 1 modules. And it's that adjunction that I want to look at. So I will call that Q for quotient. It's the indecomposables quotient, or the homotopically made up version of indecomposables. It lands in alg J, and J algebras are at least equivalent to tau 1 of O algebras. So the reason for this sort of technical sidestep is a neat little trick that, since this is a cofibration of operads, this guy U will preserve cofibrant objects. So I think this is due to Resk or perhaps Catherine Hess somewhere in the literature. And what I mean by saying that this is a model for the stabilization is, of course, that, oh, that is red. The default color obviously should be purple. Is that the suspension spectrum of an O algebra is equivalent to the left-derived functor of Q applied to X. And this guy we refer to as topological Quillen homology, or analogously as the homotopical version of the indecomposables quotient. So sometimes you see this as derived indecomposables. And similarly, if I start with a O of 1 module, then I can say that, well, the underlying loop space in this case is just the right derived functor of the forgetful functor. In the case where O of 1 is just S, this just gives a spectrum, a trivial O-algebra structure. Cool. So with this understanding of what suspension or what stabilization looks like for O-algebras, there's actually a calculation due to Harper-Hess of the layers of the tower. So dn of the identity in alg O, well, it's the fiber of tau n, circle over O to tau n minus 1. And it's also of the form U of O of n smashed over sigma n with, all right, just Q of x smashed n times. And this should look a lot like the classic version from Goodwillie. This is my suspension spectrum smashed n times, and this is my underlying loop space. So in particular, what this tells us is that O of n, this guy right here, this is a model for the nth derivative of the identity on alg O. If I have it sitting in the right spot, I can take cross effects and sort of peel this coefficient off, and bam, there it is. So it's a model for that guy. It's equivalent as spectra with a sigma n action.
Sorry, Duncan.
Yeah.
Out of curiosity, you mentioned that this calculation is, well, right, it has the same shape as the original result for topological spaces.
Yes.
Does it follow the same proof as well, or were very different ingredients involved in that calculation?
Yeah, so it is quite different, actually. At least in the case where, so in this case, my functors that I'm taking exciso approximations look like some bimodule circled over O with blank. And it turns out that whenever I'm in that sort of situation that, well, at least in this case, dn of the identity is going to be of the form in of O circled over O with blank, where in is just concentrated at level n. And then based on how the circle product acts, you can show that the only O actions on this thing are from O of 1. So then you can say, this is in of O circled over tau 1 with tau 1 over O of blank. There's my indecomposables, and then you can describe this thing as a smash product.
Sorry, Duncan, I have a question.
Yeah.
So you're working in some category of ring spectrum?
Yes.
So alg O is like a category of ring spectrum where, it could be like A infinity or E infinity or whatever.
Correct.
Okay. And then your things there that you lower down on your page, if you could go down where you were talking.
Yes.
Yeah, so those things lower down still.
Yes.
Those things, the ON there in that formula are the same ON that are in like the structure operad of that kind of.
Yes, exactly.
Oh, okay, I see. Okay.
Yeah. Right. So if this is like commutative ring spectra, then this is just an S everywhere.
And Q of X is what?
Is the topological equivalent homology. So this should really be the left derived functor of Q, but it's the indecomposables quotient. It's whatever stabilization looks like for your algo category. Or I should say suspension spectrum looks like in your algo category, which.
So you mean that algo is like some kind of, it's like a model category or something like that?
Yeah. I guess I did sort of brush this over.
And then you stabilize, there's some like general stabilization procedure.
Yes. So it's tensored over a simplicial set, so you can build at least, sequential spectra on it and show that Bousfield-Friedlander spectra of category of spectra is equivalent to just modules over the O of 1 term in your algebra.
Okay, thanks.
Yeah. So any other questions? This is sort of a good time to to pause anyway. Cool. So this calculation tells us then that, well, in the same sort of thing as before, I have this derivative. I expect the derivative to be here. It's sort of telling us that this term from the operad O is a model for our derivatives. Well, remember Michael Ching's work that says the derivatives themselves in the category of spaces has an operad structure. So I have something that in a different context, which feels very similar in some ways to working in O-algebras, something which is an operad. And then I have some terms there which are from an operad. So the natural question to ask is, well, is it possible to give, well, I won't say give, that's the word I don't want to use, to endow, is pretty much the same word, the derivatives of the identity in O-algebras with an operad structure that recovers that on O. So this is sort of a subtle question because, obviously, well, if they're equivalent to O, then I can just say, just make it, just make it an operad that way. But what we're looking for here is some sort of intrinsic way of constructing this operad structure. So something that generalizes to other contexts, which the constructions I'm about to give here, I have also shown they produce an operad structure on the derivatives of the identity in spaces, and are sort of suggestive of a way of producing a more general operad structure on a suitable category for doing Goodwillie calculus. So this is sort of a, not just a, like a ad hoc approach, but really like something that functor calculus sort of is born knowing about. So right, the answer here is yes. That's due to me. I should also mention that Ching has a completely different way of going about this, but also has a proof for this statement. His is very much dependent on working in infinity categories with infinity operads.
Excuse me.
Yeah.
So if you have forgotten the structure, does that mean you can remember or recover the structure?
Yeah. So it's like this sequence of derivatives is going to be equivalent as an operad, well, as a fattened up operad, but let's just say as an operad to O itself. So they're going to just be sort of equivalent monoids. So it remembers everything about the original operad.
So the point is the extra, it's not just the spaces or the objects, you need all the composition maps.
Exactly, right. It's like I could take a space and take its homotopy groups and then just do like a product of k pi whatever's, and it's going to have the same homotopy groups, but it's not going to have the same sort of extra algebraic structure that perhaps your original space had. So this is really just the same object.
And sorry, just a question on what you said about having degree-wise equivalent objects. Let's say you have a symmetric sequence that is an operad and which is equivalent to another symmetric sequence that doesn't have an operad structure, and you try to just transfer the operad structure. It feels like at best you would get some kind of infinity operad structure, right?
Yeah.
Because I mean, those are strict monoids in symmetric sequences. That doesn't feel homotopy invariant to me.
Right,
So
right. You're going to end up with some zigzags at some point, probably, and it's going to, yeah, it's right. Just being equivalent to an operad level-wise doesn't necessarily mean that you should expect to be an operad. You might end up crushing too much information by your
right, but you could probably get some, I don't know if it's an infinity operad structure or some homotopy invariant version.
Yeah, I would definitely believe so.
Okay. But your point here is that you're not trying to transfer through an equivalence. Okay.
Exactly. Yeah. The sort of constructions are inherent to functor calculus themselves.
Got it. Thanks.
Cool. All right. Cool. So, right. So this brings me to part 2. So that was the whole crash course in functor calculus leading up to the statement of this question. Part 2 is how to induce, I'll say homotopy coherent John would want me to say highly homotopy coherent monoids. So there's a secret weapon in my arsenal here. So the secret weapon is the box product. So there's probably, you know, 1,000 things called the box product. So what box product am I talking about? Well, I mean the box product for cosimplicial objects as described initially by Vatanen, but perhaps made more popularized by McClure-Smith in their solution of the Deligne conjecture. I think they have a couple papers where they use this box product to do some interesting stuff. So, well, what is it? Well, it's a monoidal product for cosimplicial objects. And it's defined as follows. So if I have, let's just say, cosimplicial spaces, so x and y in top to the delta, these are just, you know, functors from your ordinary simplex category into top. Well, one thing I can do is I can just multiply them together. Get stuck on eraser mode sometimes. X times y down into top. And then use a monoidal pairing on top to map into a single factor. Or what I could do is, well, these are, you know, finite totally ordered sets. So I can take two finite totally ordered sets and concatenate them. This has r plus 1 and s plus 1 elements. So this will land in r plus s plus 1. So it's the concatenation functor. Concatenation. And all right, well, I'm going to set up where it looks like I can take a con extension. When I take the left con extension here, that's what the box product is. Great. What does that actually mean? Well, I think the sort of most illuminating use of the box product, and the one that feels like kind of a hilarious amount of overkill, but is extremely illuminating, is the following example. So if I have a pointed space, then I think, you know, everyone is knowing that the loop space on X is a monoid. And well, it's not a strict monoid, it's a homotopy coherent monoid. It's an A infinity monoid. I can take two loops and I can concatenate them, and now I have a new loop. Well, that's not exactly monoidal because there's some choice of switching around where you make the concatenation point, but I can do that in a coherent way to make this into an A infinity monoid. So that's a proof that it's an A infinity monoid, basically. But you know, what's one way of getting at the structure? Well, proposition sounds a little too formal, but okay, I jumped the gun a little bit. Well, one way I can model the loop space is as the following. So I can model it as the totalization of a cobar complex on a pointed space with respect to the diagonal map. So let's put all that in writing, and then I'll explain what's going on, etc. Okay, so this is a cosimplicial object. It's meant to just be the cobar with points on the end and x in the middle, and the cobar with respect to the diagonal map giving me my comultiplication. So what are these coface maps here? Well, the outside D0 and the D last maps are just the inclusion of the point into X. And for instance, here, the middle coface map D1 is just this diagonal comultiplication. We, of course, have codegeneracy object or maps. This is a full cosimplicial thing, but I'm going to work with a modified version of totalization called restricted tot, which gives you the same thing. It's just a little nicer to work with, so we can actually forget about the codegeneracy maps in this case, but they are just given by take X and just crush it to a point. So what about this thing? Well, let's call it C of X just for simplicity. And the proposition is that C of X admits a pairing with respect to this box product. So there is sort of a pairing. In fact, this thing is a monoid with respect to the box product. The box product gives you a monoidal structure on cosimplicial objects, as long as your category is symmetric monoidal and probably you want closed. So how is this induced? Well, we said what the box product is, but it doesn't really tell you how to work with it. There's some nice diagrams you can draw, but I'll just sort of say that it's induced by giving coherent maps. There's some ways that they have to agree, but it's not too restrictive, out of the following. So I need to go from the level P cross level Q into level P cross Q. And really, this box product does a very good job at taking a cobar resolution and turning it in, hitting that with toe, and then that becomes a monoid. Because if I look at this cobar, it's exactly cooked up that, well, what's level P here? That's just XP. What's level Q? That's just XQ. And there's a very natural isomorphism into XP plus Q. Just include the first P and the last Q factors. So this induces this pairing, these maps, induced by blah. All right, well, so we have this monoidal pairing on the box product itself. How does this give us a pairing on the loop space? Well, we know that the loop space is equivalent to Holim over delta of C of X. That Holim over delta, again, is equivalent then to the tote of C of X. C of X is, I'm working in spaces, so this is, well, it's not, maybe not redefibrant, but when I work with this tote restricted, I can get away with just level-wise fibrant. And certainly spaces are level-wise fibrant, so we're good to go. And tote I can model as I'll write map, the end of maps from the topological simplicial object of simplices into C of X, like so. So if I wanted to say describe a pairing loops cross 2 down to loops, well, I can do so as follows. I can take, an alpha and a beta. I can represent them by functors from delta into C of X. Here's alpha, here's beta. I can take these guys and box them together and post-compose with the monoidal pairing on C of X. And if I wanted a third loop, well, I'd be looking for something like this. I'd be looking for a map from delta into C of X. Let's call it gamma. And, well, I could just pick some precomposition here. It turns out that you can actually just calculate what is delta box delta. You can just calculate it from the definition of what makes up the nth level of this, and it's homeomorphic to delta at that level. So there's some contractible space out front here, which modifies this guy and gives you your A infinity operad structure. So here AN is the sort of coendomorphism operad on delta. So it's delta box N. And, well, both of these things are contractible, fibrant, cofibrant objects, so it's a contractible thing. So that's maybe not, the way that you would have thought that the loop space is given an A infinity monoidal structure, but it sort of illustrates the idea behind what I'm going to do next. So I think this is just super cool. Basically, I don't know, this McClure-Smith paper, I think, is like one of my favorites, just because it's just such a cool construction.
In my algebraic topology class, I introduced loop concatenation just a few days ago, but I should have introduced it that way.
There you go. I think that's clearly the better choice. Okay, so this brings me to part 3. So we're going to put these two together. So my aim is to induce some sort of operad structure, and operad is a type of monoid. So part 3 is about how to induce this operad structure for the derivatives of the identity. Well, this box product is our secret weapon, and it's telling us, it's suggesting that we look for a cosimplicial object, perhaps even a cosimplicial object which either is or is extremely similar to some type of cobar resolution on a comonoid. So let's see what we get. Well, the main idea is really coming from this paper of Aron and Kankanrinta, where they analyze the derivatives of the identity in spaces via the stabilization adjunction. So let's just recall alg O, the stabilization adjunction to alg J. Well, these guys are called Q and U. What is Q? Well, Q is sort of this guy. It's the change of operads adjunction, change of rings adjunction, or the left adjoint from that. And anytime I have an adjunction like this, I can build a cosimplicial object. So I can take the identity functor on alg O, and I can resolve it by stabilization. So here's the unit map. I can apply the unit before or after, get UQ, UQ, etc. And again, we have code degeneracy maps, but since we're working with tote restricted, we don't have to necessarily worry about those guys. And I'll just refer to this as UQ bullet plus 1, where bullet is the index of my cosimplicial thing. Now, if I'm going to do functor calculus, I want to sort of know how the identity functor interacts with this resolution right here. So this is a very nice theorem due to Jake Blomqvist that tells us if I have a k-connected, oops, I should say where it is, an O-algebra, which is k-connected, these are spectra, I just mean k-connected as a spectrum, then we know the following. So then x into, I'm going to write something here, and then I'll explain what it means, holim less than or equal to n minus 1, uq bullet plus 1 applied to x is n plus 1 times k plus 1 connected. So what is this guy right here? This just means take your cosimplicial object, go up to level n, and then chop it off. So now I have some sort of truncated cosimplicial object, and it only goes up to the level, well, n minus 1 in this case. So I get these strong connectivity estimates on comparisons from identity, this co-augmentation, into truncations of this cosimplicial object. And it turns out this is enough to induce an equivalence, Pn of the identity on alg O into Pn of holim less than or equal to n minus 1, uq bullet plus 1. So this is agreeing to order n. You can sort of think of this as like, I have some two functions that for, near a point, then f minus g is some constant times x minus y to the whatever power. And that's enough to give you an equivalence on polynomial approximations. Same idea works in functor calculus. And well, there's a technical thing here. I have a homotopy limit. I can move the Pn past it because this diagram that I'm working with is some very finite. It is a diagram whose nerve has finitely many non-trivial cells. So this is equivalent to the homotopy limit of same diagram, and then I take polynomial approximations level-wise. So this ends up being extremely useful. So Pn of the identity was nice, but Pn of stabilization is even sort of easier to work with. And this is especially true in spaces. The same sort of idea works, and it really tells you where this partition Postset complex is coming from. But we're in O-algebras here, so we'll continue with this story. And well, it similarly holds for homogeneous layers, and then also for taking derivatives themselves. So what is this going to mean for us? Well, let's just write out what the UQ diagram is in terms of the change of operads adjunction. So UQ bullet plus 1 is the diagram as follows: J circle over O with blank. There's two maps into J circle over O, like so. Three maps into J circle over O, like so. Dot, dot, dot. What are the coface maps? Well, you can identify them with, for instance, D0 is, I can stick an extra O in front, O circle over O, like so, and then O maps down to J. So this maps down into that. So there's where these coface maps are coming from. And this gives you a well-defined cosimplicial object. And what this corollary tells us is that if I want to take the derivative of the identity functor, the nth derivative, that this is going to be equivalent to the homotopy limit over delta of the following. So j at level n, j over O at level n. Sorry, I meant to put something right here, so I'm going to finish drawing this diagram and then say what I meant to put. So derivatives of functors of this type, whenever I have some bimodules circled over O with blank, are characterized by Kuhn-Pereira. They show us that the nth derivative of something of the form m circled over O with blank is just equivalent to m at that level n. And it's functorial in this bimodule. So taking derivatives of a diagram like this is just sort of the evaluate at level n for the part left of the final circle over O with blank part. Great. So this guy right here defines for me a diagram, which I will call C of O at level n. And then by looking at all of the n's together, I get a cosimplicial symmetric sequence. It's level-wise fibrant because I'm going to work in EKMM spectra where everything is fibrant. So the derivatives of the identity are going to be modeled as the totalization of C of O. Now, this diagram here, we sort of saw before that I'm looking for some sort of cobar resolution kind of thing. Well, it's kind of defeating the purpose of the box product pairing, but this does look a lot like a cobar resolution. Cobar J circle over O, J, where the monoidal product is into circling over J. Well, the problem with that is J circle over O with J is a model for the bar construction on O. And that is supposed to be a co-operad, but actually defining a strict model for the co-operad structure maps on it is quite tricky, and perhaps maybe only possible up to homotopy in certain cases. So it's basically a cobar resolution, but actually describing it as such sort of ends up taking more effort than just working with this diagram here, which is sort of like level-wise equivalent to a cobar kind of resolution. Okay, so this is our model. The derivatives of the identity are given by the totalization of this cosimplicial symmetric sequence. And here's the theorem. So theorem due to me, part one says that, all right, well, what do I need to know? I need to know that there is some type of pairing, C of O down to C of O, which is monoidal in some sense. This ends up being, actually constructing the pairing is not bad, but I'll say a remark about it before I construct it. This ends up being extraordinarily tedious because I'm working with the circle product. And if you've ever worked with a circle product, it's not a closed product, and it doesn't commute with colimits in the left-hand variable. And this ends up being kind of a big headache because the box product gives you a monoidal product on cosimplicial objects. If you start with a closed symmetric monoidal category, it turns out you can still make it work in this setting where you're not necessarily closed. It's just you have to do a lot of sort of combinatorics and sort of piecing apart the circle product. So if you ever are interested in looking at my paper, there's a large part of it that is dedicated to making this work. But the moral is that it does work with enough sort of, manhandling. So how is this pairing constructed? Well, just like before, I look for some sort of compatible pairings. This should be circle. It's with respect to the circle product. Like so. So I'm looking for something C of O at level P, circle C of O at level Q into C of O at level P plus Q. Now, if I look at what those things are, well, at level whatever, I have that many plus one J's. So this guy looks like, J circle over O with J, circled with J circle over O with J. I have P plus one J's here. I have Q plus one J's here. Well, what I can do is I can just pair those J's off J is an operad. It was factored in the category of operads. So I can just use the map J circle over O, J circle with J down to J and land in something that has P plus Q plus 1 J's in it. So this pairing is induced by the almost natural, still pretty natural, extremely natural pairings on J. In the case where O of 1 is just a symmetric sequence, these are just fattened up versions of the identity, basically. So it's induced in a very natural way, just like the Kobar example with a pointed space.
Time to conclude soon.
Okay, cool. Yeah, I'm just almost at the punchline here. So, right, and great. So this guy induces the which induces I'll say homotopy coherent operad structure. So that's where the homotopy coherence came from, way back at the beginning on the derivatives of the identity. And well, the second part is saying, how does this relate to O? Well, if I look at this diagram that defines the derivatives of the identity, there's a natural co-augmentation to C of O, just given by the map O down into J. So there's a co-augmentation O into C of O. So, something that co-equalizes the first two maps. And whenever I have something of this type, well, this is a map of cosimplicial objects where I stick a constant cosimplicial object on the left. And it turns out in this framework of homotopy coherent operads, I can just take an operad and just include it into homotopy coherent operads. And within this larger class of homotopy coherent operads, this co-augmentation induces an equivalence O to derivatives of the identity on AlJ as homotopy coherent operads. And that's where you sort of get these things being equivalent. So I'll just close by saying two things about applications. So applications, well, all right, just one thing actually. Similar pairings work. So similar pairings produce, I'll just say similar techniques produce homotopy coherent operad structure on the derivatives of the identity, not in AlJ, but in spaces. So if you've ever looked at Michael Ching's paper where he constructs this, it's quite a lot. There's a lot that goes into it. So one of the hopes is that this sort of streamlines maybe at some level this construction and gives you sort of more of a user-friendly approach to working with algebras over this thing. So within this framework, I can say, I can actually produce a strict map from topological spaces, which lands in algebras over this thing, and sort of work with this in a really sort of nice way. So I will end there, and thanks again for having me.
Thank you for the very nice talk. Let's unmute ourselves and thank Duncan. Are there any questions? Well, if I may, I did have a question.
Yeah.
Which flavor of homotopy coherent operads are you working with here?
Yes, so this is
if
actually,
you don't mind
yeah,
lifting the hood and jumping into some technical details.
So this is something that I have cooked up. So this is I guess it's a new construction. So what it does at the core really is it consists of coherent maps of this type. So like an operad, right? Like an operad has maps where you do O of n, and then you have a bunch of stuff like k1 through kn, and then you map into the sum of the k's. And what I've done is I fattened up these maps in a equivariant way even. So I fattened this up by adding some term here dependent on n and k. So n and k1 through kn, which also encodes the equivariance that you would expect to have for this thing. So like your operads have symmetric group actions. So this thing should have a sigma k action, and that should sort of decompose on actions here and on the n. And that all sort of gets taken into account as well on the A factor. And this fattened up operad is coming from the same place as the A infinity monoidal structure on the loop space. So it's really just sort of a fattened up version of this thing, where then I sort of freely add some symmetric group powers on the outside or on the inside. It ends up giving you sort of the same thing, which encodes the equivariance that you would expect this map to also have.
Are there
And then,
are there other sources of such homotopy coherent operads in nature, other than from your theorem?
yeah, so the way that I know how to induce them, they're sort of specifically cooked up to encode things that get induced by this box product. So I think it ends up being very specific to, if you want to induce an operad pairing, well, it can be quite difficult to actually just construct operad maps. So one way of doing it is by these the idea is that in order to induce these operad maps, in this case, I'm going to work on the level of resolutions, and then you sort of lose strictness when you hit them with toe, and this is just a way of keeping track that strictness. And I haven't proved it, but I'm almost positive that these things can be given a model structure, and within that model structure, this A infinity operads it's just equivalent to just good old operads. So
yeah, I was wondering about some strictification results.
Yeah.
You're guessing that there is such a thing, but
yeah, I'm guessing that there is, and I'm guessing that the way to do it would be to take my advisor John Harper's work, his thesis work, and translate it into this framework and just do it there. And that sounds like a tremendous headache, just because it's already like super complicated, just like how he does it to actually get a full model structure. So I have just sort of put that on the back burner for now, just because.
fair enough.
Yeah.
All right. Any other questions, comments?
Something more naive in the same direction. So these A, N, K1 up to Kn, those things are they're equivalent to like S0 or something like that?
Yeah, the sphere spectrum in this case, because these are all spectra, but like this thing should be equivalent to S, or perhaps it should be equivalent to some like co-poweredness of S, where that co-power takes into account the correct equivariance. But it's just the co-product of S's, basically.
It's like whatever the monoidal identity is equivalent.
Exactly. Exactly.
But can you and then they have to have some relationship with each other, is what you're saying as well?
Correct. Right. And actually encoding that, well, it's all sort of clear. Like if you write it down, you're like, oh yeah, that's what it should be. But actually making that like work and writing everything down, like if nothing else, your indices just explode. Like you're just suddenly working with like just too many. It's like just so many indices. But it can all be sort of taken into account, and these guys right here are sort of, they have to agree in some sort of coherent way. It's actually kind of interesting how it all works out, and yeah, at least for the strict, I call this an n colored operad with levels, because I have to sort of give them levels in order to take into account how many iterates of the circle product I'm working with. It's very closely related to like categories of trees, if you're familiar with working with these. But if you work with the actual strict n-colored operad with levels that gives you operads, then all of its composition maps on itself are just isomorphisms. And it's just an isomorphism that says the circle product sort of behaves in the right way. And then this just says, well, now your circle product is just sort of fattened up in a coherent way.
So can you change, well, this is kind of the question, like this is just a naive kind of version of what you were saying maybe, but like, can you change the ONs to like incorporate these A's? So you know, it's a different, but that's like just another way of kind of strictifying it, but not strictifying the actual thing itself, but adding the A's into it somehow and making it strict that way. Like, for example, you can adjoint this over to the other side, I guess. Can you adjoint that A in over to the other side somehow? And then, I don't know, something like that. I don't know.
Yeah, it's right. So I think I see what you're saying. I mean, this guy is even particularly nice in that this fattened up guy, which encodes operads, actually comes with a map down to strict the thing that encodes strict operads. So one way to actually to strictify an operad would just do the change of colored operads adjunction applied to this, which is something I've worked out. So basically, it would just say, you know, this A of n is sort of these mapping spaces, like some co-powered version of these mapping spaces. And if you just sort of choose the one that is like as nice as possible, basically just like an identity map on all these mapping spaces, that should be the canonical choice of strictifying one of these homotopy coherent guys. But I don't know how to sort of make that fully precise, I think is I don't know how to make that fully precise without having to just sort of do it in like the most general setting. And in that case, it would be, I think, just
I guess since it's equivalent to a strict operad, that's what you're saying. So that's a strictification. So.
Yes, yeah. So it's basically like this operad is described. I'm going to end up using the word algebra and operad like a lot. So this operad itself is described as an algebra over a colored operad, and a colored operad who's colored by the natural numbers or sequence of natural numbers.
Yeah.
And when I can take it, so that thing has sort of an action map like so, and I could always compare A with the strict guy, and then I could just sort of do like, you know, I call the strict guy Oper with an underline. So some version of that thing should be a strict. Like if I have, you know, a monoid, an A infinity monoid encoded by some A infinity algebra or operad, and that A infinity operad actually comes with a map down to the commutative operad, or I should say associative operad, then one way to strictify it would just be to take, you know, the change of operads adjunction associated to this comparison. And there's a very natural analogy in this fattened up operads world.
Any further questions? If not, well, let's thank Duncan again.
Thank you.
And thank you all for attending.